All right, so here's a device called a ballistic pendulum, and I'm going to show you a video of that. You can tell based on its name, okay, what a ballistic pendulum was used for and still can be used for, is to find, let's say, the speed of a bullet before you had a high-speed timing device, like a photo gate or something like that. Okay, so you could take a rifle, fire it into a block of wood, okay, so the bullet embeds itself quickly in the block of wood, and it swings up to a certain height that you can measure, all right, and then it'll eventually swing back down. That's why it's called a pendulum. All right? So you're trying to find the initial speed of the bullet. Okay, so here's my before picture for the collision. The bullet's about to hit the block, right? And then in the after picture, okay, for the collision, this is my after picture, okay? So the bullet collides quickly, right? It doesn't happen over a period of 3 or 5 seconds. It happens quicker than that. So the bullet collides quickly with the block, and they both move off with one common speed, capital V. Okay, so they both move off with one common speed, big V. So that's my collision. So I'm going to conserve momentum for my system. So initial momentum is mv0 just for the bullet. Final momentum, okay, that's why we need the picture. Picture shows them stuck together. Okay, so there's little m and that's big M. So remember, momentum is mv. Okay, so when I write P final, it's both masses stuck together times that capital V. Right? Now I'm trying to find little v. So if I don't have a device that measures the speed of the bullet, I certainly don't have a device that measures the speed of both of them together. So to be able to find little v, I need to find big V. Okay, and then what we do is we apply conservation of energy. All right, but we can't conserve energy from here at the beginning, okay, from that point to this point, right? Because the energy the bullet has here is kinetic. Okay, there's kinetic here. Over here, it's all potential energy because this thing swings up, momentarily comes to rest before it swings back down. So here the bullet has kinetic energy. Over here, the bullet and block have potential. Okay? But the problem is energy is not conserved for the system because what type of collision is it? It's an inelastic collision. Okay? It's an inelastic collision. Okay? Now, how do we know it's inelastic? Well, because definitely these things stick together, right? So you could also call it a completely inelastic collision. But the reason you know it's inelastic is because you have friction. So when the bullet collides with the block, okay, the bullet has to drill a hole to eventually stop. So while the bullet's drilling a hole, you have these huge kinetic friction forces that cause the bullet to stop in the block. Okay, so that would be like taking a drill and drilling into a block of wood. If you take a drill and drill it into a block of wood, okay, when you're done, the drill bit gets really hot, the block of wood gets hot. Okay, or just take your finger and rub it really fast on the table, your finger's going to get really hot and start to burn. So most of the kinetic energy of the bullet is lost in the form of heat in drilling the hole. So this kinetic energy here is not equal to the potential energy there. Most of the kinetic energy is lost in the collision in the form of heat. So what we have to do is we have to apply our energy expression, E initial equals E final, after the collision. So right after the collision occurs, both of these things start to move off with some common speed, big V, so they both have kinetic energy. And then up here, you have potential energy. So we conserve kinetic energy after the collision. Now, we had an expression that change in energy is equal to the work done by non-conservative forces, okay? Well, you have the string force, okay, you have the tension in the string, but the tension in the string does no work, whoops, because it's always perpendicular to the direction this thing is moving. And we think we talked about that in the Tarzan problem, okay? All right, and you do have, remember the gravitational force, and gravity does do work, but the work done by gravity is wrapped up into the concept of potential energy. So mechanical energy is conserved after the collision, okay? So in my picture, I wrote my initial energy, potential and kinetic, final energy, potential and kinetic, and I had to pick a reference point right there for potential energy, okay? So initial potential energy is 0, okay, at this point here. So PE initial is 0, because that's my reference point. Okay. Initial kinetic energy is this. Okay. And remember, the picture shows they're stuck together, so that's why I have both masses. Okay. And capital V is the speed with which both of them start to move, right there. Okay. Final kinetic energy up here, whoops, K final is 0 because it momentarily comes to rest. And the final potential energy, okay, is mg times that height. Okay, but remember, they're stuck together, so it's capital M plus little m. Okay, so these masses drop out. Okay, the same on both sides. So that gets me capital V, and that's what I get to put back into, I call this equation 1. I called that number 2. So I take 2 and put it back right there into number 1. So here's number 1. So MV0, okay, and right here, that was capital V, and I put that in, and I can solve that for little v0. Okay, so all I need to be able to find, okay, if I want to find the speed of a bullet, fire it into a block, okay, if I don't have any high-speed electrical timing devices, all I need is the mass of the bullet before I start the experiment, measure the mass of the block before I start the experiment, little g, that's in our chapter 2, or this semester we'll see a couple ways to measure little g, okay, that's easy to do, and then you just measure the height, and the video shows one way to measure the height. I think there's a picture of a grid back here. Okay, you can actually measure how high this thing goes up. Okay, some of the devices, you have a little ratchet here. Okay, and when this thing swings up, there's a little plastic thing that stops right there. And when this thing swings back, that little plastic thing stays at the angle, then you can read the angle. And then you could use trig to find out the angle. Well, you could use trig to find out h. Okay, so that's a use of a ballistic pendulum. You could find the speed of something that you otherwise don't have a device to measure. Just fire it into a block.